So with that, like I said, please ask questions as they come up, but I'll jump right into things. First, a little bit about Aerotas. We do drone data processing for land surveyors and civil engineers since about 2014, which makes us a very, very young company in the world of land surveying, but also a really, really old company in the world of actually working with drones. And we've seen the huge run up in popularity with drones, and then everything kind of crashed a lot, and people started realizing that, oh, they're not just cool, shiny toys. They actually are nice, boring pieces of survey equipment. And that's how we treat them too, is boring, repeatable tools that you can use as part of your job as a surveyor. We work with land surveyors and civil engineers exclusively throughout the entire United States, helping do drone data processing, both photogrammetry and LiDAR, as we will be talking about. While we certainly are most known for working in photogrammetry, we do process LiDAR data as well. And it's all of the examples that I will be talking about today are actually real live projects that we've done in merging both photogrammetry and LiDAR data together. A little bit about myself, my own background. I am the CEO and lead photogrammetrist of Aerotas. I actually came initially, a lifetime ago, from a background in finance and statistics, and then working in finance and statistics, and then eventually getting out of the world of finance because you don't want to actually work there, trust me. Working in statistics got me into photogrammetry and surveying from kind of the mathematical statistical angle. I am an ASPRS certified mapping scientist. There's my certification there to the right. And so I very much focus on, and what I really love is the data side of this, and doing a lot of those statistical analyses and workflow analyses between photogrammetry and LiDAR is something that I actually have a lot of fun with. So getting all of the data and information to go into this presentation has actually been pretty fun for me. But first, what we're going to cover today, we are actually going to cover kind of a couple of different main objectives. For starters, we're actually going to discuss the state of the art of drone LiDAR technology and what's out there. Obviously, LiDAR data and LAS files and point clouds have been around for a while, but if we're talking workflows, the technology that you actually use to integrate into that workflow is absolutely critical, not just the end data. Even if the end data is identical, if one workflow can get you there with $5,000 of investment and 10 man hours, that's going to be a heck of a lot better than the exact same data with 100 man hours and $100,000. So talking about the technology is important to making sure that your workflow is smooth and cost effective. Then we're actually going to go into drone photogrammetry technology as well. Now, while this is about merging LiDAR and photogrammetry, photogrammetry has almost become, I don't want to say old hat in surveying, but you've probably seen other presentations about it. I know there are other people even at this conference that were talking about photogrammetry, but it's important to get the fundamentals of photogrammetry technology as well, because if we're going to be combining these workflows, understanding the steps of photogrammetry will get you to understanding the steps of LiDAR and how to merge it all together properly, much better and much more efficiently. And then we will go through your LiDAR and photogrammetry workflows, how we actually blend them together. But first, let's talk about something that you've probably seen me say before, which is that if your drone program isn't saving you time and money, then it isn't working. We focus on creating a drone program that is not a research project. It's not what we call a high school science fair thing. It's something that actually saves you time and money. This isn't about a toy. There are lots of toys out there, and if you want to spend hundreds of thousands of dollars on laser-based toys, you're welcome to. But then we'd be the wrong company to talk to, because we really focus on saving time and money with all of this stuff and to getting a good drone program. And that's what all these workflows are going to be about. A lot of our workflows and discussions are about efficiency, not just how do you get the highest quality data, but how do you get the highest quality data in a way that is time effective and cost effective for you. And that's because a good drone program, whether it's photogrammetry or LiDAR based, it ought to, well, for one, increase your flexibility, allow you to do new projects, serve as a force multiplier, scale up and down based on need. LiDAR is increasing the flexibility even further, because projects that couldn't be done via photogrammetry and still had to be done on the ground, well, now they can be done via LiDAR. LiDAR really expands the envelope of where drone surveying and aerial surveying can go, because it has the capability to penetrate vegetation a heck of a lot better than just photogrammetry could. serve as a force multiplier, and scaling up and down should be pretty familiar to anyone that has worked with aerial surveys before. You can survey hundreds of acres in the amount of time that it would take to do a topo of just a couple of acres before. It should save time and money. It should take considerably less time and manpower in the field and reduce overall costs. We make sure, though, with our workflows that you don't just wind up trading field time for office time. Because if you save 10 hours of field time, but then you have to spend an extra 10 hours of time in the office processing it, well, that doesn't actually work out too well. And at the end of the day, it should actually get you better deliverables than you would get otherwise. That means you should be getting the same accuracy as your traditional surveys, but with up-to-date, high-quality imagery and a perfect record of site conditions, which means you have you should be able to see everything that was there, not just where your survey crew took some additional shots, but by having the additional point cloud, the 3D model, the ortho photo, you can see everything. You can oftentimes spot places that maybe your field crew missed. And so we've been working in this world for, 6-7 years now, and we've seen a lot of pitfalls that people make in terms of creating a drone surveying program. And this is even more true with LiDAR than it is with photogrammetry or drones altogether. The first thing is, don't use the wrong tool for the job. LiDAR and photogrammetry as well are wonderful, amazing things, but they are a tool. You cannot do everything a surveyor can do with a drone. A drone is not about to replace a surveyor in the field, not even close. The drone should be one tool in the surveyor's toolbox, along with total station, GPS, maybe your scanner, and heck, even a traditional airplane still absolutely has its place in a surveyor's arsenal of tools they can pull out. Also, don't ever overspend on gear that you don't need. Man, with LiDAR, you could spend a whole lot of money on LiDAR and get a whole bunch of gear that is not right for you and is not exactly what you need. Drones, computers, software, all of that can be very expensive. And like I said before, when we're talking about workflows and efficiency and us trying to save time and money, if you want to spend $250,000 on LiDAR, you can. But if we can get you the same deliverable for 40 or 50 grand worth of hardware, well, that's the direction that we're going to do. So don't overspend on hardware. It's a common pitfall. A lot of people think newer, bigger, shinier, and more expensive will get you better results and have a better workflow, but that's not the case. And that's part of what we're talking about today, is how to not overspend on the gear you don't need. Likewise, don't spend too much time in the office. Many people think that LiDAR is the most magical solution to surveying, or even they thought the same thing about drones, that it was absolutely magical. You fly a drone and you don't need to survey anymore. And then they realized that without a good office workflow, you're actually going to be just collecting, you're going to be spending so much time cleaning the data, extracting the data, creating tin surfaces, converting from one file format to another, that it doesn't work, and you wind up not using it very often on projects because you're spending too much time in the office. Get the data you need, only the data you need, and then get out. That's what we say. And lastly, don't treat this like a research project. A good drone program, from our opinion, is boring, repeatable, and efficient. The first time that we were flying drones for surveying purposes, everyone in the office wanted to come out. And then when they saw that you just push go and it goes up and it flies, just kind of buzzes silent, like almost silently in the distance, comes back and land, it's really boring. Sure, the first time you fly a big LiDAR survey drone, it's exciting, it's big, it can make heavy and makes all kinds of buzzing noises when it takes off. But I promise you, by the 5th, 6th, and especially 50th and 100th time you wind up flying a drone, boy, it is a real boring technology. And that is a good thing, because it's reliable. It gets you what you need. And because what you need at the end of the day is a survey. This is a survey that was flown partly with drone and shot with a lot of other data on the ground. And in fact, our moderator, John Luckow, that's his seal here in the corner with Arizona Surveying. So they are a great company and have been working with us for a while. So I've gotten to know John, great guy, and we're happy to be partners with him. But this is what a survey looks like. And this isn't a drone survey. This is a survey. Specifically, it's an ALTA survey. And that's what your clients want. They don't want a LiDAR survey, usually. Sometimes they do. But most of the time, they don't care about that. They want a survey. They want a topo survey. They want to know where the utilities are. They want to know the elevation changes. They want to know volumetric calculations and on and on and on. They don't care about the technology you use. And it's your job as a surveyor, part of your job as a surveyor, to pick the right tool for the job to get the client the data that they need. So we'll focus on how to get to an end survey with efficient workflows and deliverables. Now, again, for those of you that have seen me present here before, you've probably seen this slide or something similar that we put up. This is what a fairly standard drone workflow looks like. It starts with mission planning. Mission planning is the idea of planning, okay, what's your flight altitude, your overlap, what drone are you going to fly, where do you set your ground control points, how many ground control points, things like that. Pretty simple. A trained photogrammetrist or a trained pilot can do that in just a couple minutes. You go out, collect your data in the field. The drone part is just absolutely stupid simple. You just draw the polygon you want to fly, hit go. For those of you that aren't flying anything, I mean, it's no real piloting skills are necessary. You just push go on the drone. And then 3D model processing. We used to call this step photogrammetry, but now it's 3D model processing because it is both photogrammetry and LiDAR processing as well. You need to go from your raw LiDAR data, whatever the sensor that you have collects, into an actual geo-referenced, aligned, accurate, usable point cloud. But from there, you still have a couple more steps because a point cloud isn't what the end product deliverable is going to be most of the time. You need to draft your line work. You need to create a tin surface off of it. You need to extract your points, polylines, break lines, and actually make it usable. A 10 gigabyte point cloud is not a usable deliverable for the vast majority of circumstances. You need to actually turn it into a survey by extracting points and polylines. And then you need to actually finish all of it in CAD. You need to integrate all of your non-aerial data. You need to integrate your ground shots, your boundaries, all of your right-of-ways and other data that needs to be, or underground data, and put that in, format it for the client, and then sign, seal, and deliver. And that is what a typical workflow is going to look like. But for the few people that have been using LiDAR beforehand, when we see and talk to clients that are already processing LiDAR, this is what we see as the most common LiDAR workflow. They say, we're going to fly some LiDAR, and we're going to we'll fly it with photogrammetry too, and somehow we're going to actually profit out of it. But the problem is, when this is a big giant question mark, getting to this last part is pretty hard. And if we're being honest, very, very few people have actually made good profit from UAV-based LiDAR. Not nobody, but few people have, because it's a really complicated workflow and really expensive hardware. And when you spend that much money on the hardware and that much money processing each project, well, it rules out a lot of projects that can be done more cost effectively traditionally. But thankfully, there are good workflows, and better workflows will get you better results. This is what our kind of suggested workflow looks like. And it's a theme that I'll be hitting on a lot, which is during that those data processing steps in the middle is typically you want to actually process your photogrammetry data and your LiDAR data in parallel. You start with your raw LiDAR data, get your georeference point cloud, and you draft some vectorized data from that. And then in parallel, you work with photogrammetry, where you get your photos, ground control points, run through photogrammetry, get your point cloud, orthophoto, DSM, draft your vectorized data in that, and then you actually combine both of them in CAD finishing. Because LiDAR and photogrammetry, well, they both have their place, but neither one is just uniformly superior. It's a very common misconception that we see these days that LiDAR, it's newer and it's super expensive, so it's better. Well, that's actually not always the case. And I'll go into some of the data in just a couple of minutes of exactly why that is not always the case, where LiDAR actually is superior to photogrammetry and where photogrammetry still reigns supreme, and then where neither actually is the best and where you still want to break out your total station and do things on the ground before getting to that final survey deliverable. All right, so that's kind of the high-level workflow of what we're going to be going into. But next, let's actually jump into the LiDAR technology, the current state of LiDAR technology, what it looks like, and where it's going to be going in the next year from a hardware perspective, at least. So what are our thoughts on LiDAR? Well, for starters, the data quality is pretty good. LiDAR gives very good ground data, particularly in vegetation. So for those saying, can LiDAR do that? Is LiDAR good enough for surveying? Yes, data quality wise, it absolutely is. However, it doesn't live up to all of the hype. LiDAR is not perfect. For starters, vegetation penetration isn't 100%. If you're working in, very light vegetation or areas with trees where all the leaves have fallen off, then LiDAR is going to work pretty darn well. But if you're working in really dense leafy canopy or even potentially any sort of jungle or tropical environment, it's still not going to be able to see the ground. LiDAR is a laser, after all, not an X-ray. So it's not that it can actually see through leaves. What LiDAR actually does is when it's shining down, it's think of it shining almost a spotlight. And if it can find, or a really narrow spotlight at least, and if it can go through the leaves or in between leaves in certain areas, that's how it can get multiple returns back and actually get penetration to the ground. But it's not perfect. It does still need to see through in between some of the leaves, but it can't actually X-ray through them. So if you can't see the sky from the ground at all, even little bits, then there's a good chance LiDAR can't see the ground.
Hey, Logan, got a question for you.
Yes, please.
So can you describe the difference between a digital surface model and a digital elevation model?
Yeah, absolutely. So typically a digital surface model is going to be, I may even have some slides that could better demonstrate this. A digital surface model is going to be absolutely everything that is there. It's everything that creates the surface, including things like cars and trees and buildings, whereas your elevation model is going to be cleaned and focus much more on the elevation, things like your ground, and some buildings are included. It's worth noting, some people have different definitions of what is actually included. There's also a third one called a digital terrain model, a DTM, which is excluding all of that stuff too and focusing specifically on the ground. But the idea is of which things are included and which ones aren't, whether things like vegetation are actually included in the surface model, which is everything of that surface, versus the elevation model, which is actually the elevation of the ground. Jumping back into the LiDAR thoughts here. LiDAR is, like I said, the vegetation penetration isn't perfect, but also the accuracy actually isn't incredible. It's about 2 to 3 tenths of a foot vertical accuracy in real world conditions. And now that might surprise some people because you say, oh, well, I work with, a total station or various laser scanners on the ground. And the accuracy of that laser is like 1,000th of a foot. And that's true. The laser itself is accurate to 1,000th of a foot, but we don't care about the accuracy of the laser. We care about the accuracy of the entire system. And that laser is mounted on a spinning puck that is then mounted on a gimbal that's mounted on a drone that is flying and vibrating, and the propellers are vibrating. It's kicking and pitching and rolling and twisting and yawing. And it's trying to combine all of that data with an IMU and a GPS system to then measure the distance between the drone and a known point and the ground. And when you add all of that noise up together, your real world accuracy with LiDAR data is about 2 to 3 tenths of a foot. Obviously, this is a technology like any other that over time, that is probably likely to get better with increased, with newer technologies and newer ways of processing the data. However, right now, if anyone comes to you and says, oh, we're doing aerial LiDAR with centimeter accuracy, well, first of all, if they're talking in centimeters, that they don't work with surveyors. But second of all, that is just not how good LiDAR data is right now. When you actually bring all the noise in, they're probably referring to a different type of accuracy or some type of laboratory-based accuracy, not real-world measuring to known points on the surface. And lastly, with LiDAR, flight times are still pretty short, especially compared to photogrammetry, because LiDAR is heavy and it uses a lot of power. So that means that it just can't fly for as long or cover as much area as photogrammetry. So while the data quality is pretty good, vegetation penetration isn't perfect, but certainly much, 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 much better than photogrammetry. The accuracy is definitely not as good as a quality photogrammetry system. Quality photogrammetry can get you a tenth of a foot or even better on hardscape. And flight times are kind of short. And lastly, the main reason why we haven't been seeing LiDAR more often is because getting a return on your investment with LiDAR is really, really challenging. a year ago, I would say that a return on investment for LiDAR is nearly impossible, because a year ago, a true survey quality LiDAR system, that number wouldn't have been 40,000 plus. That would have been about $150,000 plus. But the prices have come down with certain systems that I'll talk about, the specific brands and everything in a minute. Prices have come down a lot. You used to have to spend 150 grand on just the hardware, and processing LiDAR data is really expensive too, because the drone LiDAR market is complex, fragmented, and expensive right now. You have to put all of these different moving pieces together. You need to get the actual laser sensor itself. You need to buy the flight hardware from a different company. You oftentimes need to buy an IMU and a power unit and a GPS system in addition to that. So then you need an integrator that actually puts all of these systems together, like this thing over here. These, we call them kind of Frankenstein things. You also then need an operator to fly it. You need someone to process the data, and you need to buy all the software for it as well. And that doesn't mean that it's impossible to do, because as you may have seen, a handful of people, and we've processed their data too, have actually gotten the data to work. The challenge is that it is an enormously complex and expensive workflow. Not that the data is bad. That's never been the issue. It's been that it's been expensive and really complicated. So I've given all of this. I said, it doesn't live up to all the hype. It's expensive. It's complicated. It's hard to use. It's really complex. So, well, why the heck is LiDAR so popular right now? Why is everyone going out saying, I want LiDAR? Some of you may have even had clients that actually say, hey, I want a survey and I want it done with LiDAR. Well, why are people actually going out and saying this? The first time I started actually talking about LiDAR, I didn't have a good answer for that. I didn't know. So I actually started having to do some research. Why is it that people, including the general public, are so interested in LiDAR? Well, and what I found was kind of surprising. For starters, there have been a handful of very high-profile technologies that have made the general public aware of LiDAR. The most popular of which is automotive LiDAR. The way that most self-driving car projects that people are working on use LiDAR sensors. And that's been such a huge interest for the investment community too, that they've poured truly billions of dollars into LiDAR research. And part of the reason LiDAR costs are coming down for surveying-based LiDAR and drone-based LiDAR is because these automotive companies like Google and their Waymo project have invested billions of dollars in LiDAR hardware R&D, making it what you need for a drone, which is lighter weight, smaller, lower cost, and lower power consumption. So that's pretty cool. There have also been a handful of really high-profile projects like this one, which is I want to say this was a Mayan ruin in either Central or South America. I apologize if someone wants to knock on me for my Central American history and not knowing exactly where the Mayan culture was. And this may not even be Mayan, so I apologize. I am certainly not a historian. But the discovery of some never before seen Mayan ruins in the jungle by using LiDAR to actually map some of these different walls and settlements was a big revelation. National Geographic had a whole bunch of articles on it. There are books on it too. That's just made the general public aware and say like, ooh, that's pretty cool. In fact, I should point out, we sometimes have people come and try and talk to us that are treasure hunters and say, I want to use your LiDAR to go find all sorts of ruins and treasure. And we say, okay, well, we don't even have LiDAR. We're a data processing company. So, and second, we're not in the business of hunting for treasure. So sorry, go maybe work with someone else. We work with surveyors. It's, well, it's fun for me, but that's me as a statistician that actually likes this sort of thing. And lastly, there is technology with the newest iPhone, even specifically the 12 Pro Max, actually has a little LiDAR scanner on the back of the phone itself, which is really cool application of the technology. And before anyone asks, I should say, no, this absolutely is not capable of being used for surveying, even though it's very cool. They use it for things like, making models of things on top of the camera, but it just doesn't quite have the range or power or accuracy that any sort of survey grade LiDAR would need. Its range is only about 10 feet, whereas the drones that we're talking about should be going 200, 300, 400 feet in range and still get very, very high levels of accuracy and high enough point densities. So it's another just one of those things that's making the public aware of it, even though it's not actually applicable for surveying at that technology. But really, a lot of people just want to work with the most cutting edge technology out there. They hear LiDAR. It is a cool sounding technology. It can do cool things like on your iPhone and cars and Mayan ruins. And oftentimes people are willing to pay for it. And that enough for you guys, if your clients are willing to pay for LiDAR, that very often is enough of a business case for you to invest in the technology as well and start becoming more proficient at it. But really, LiDAR does have its unique advantages too. It absolutely does have a place in a proper surveyor's toolkit. And the biggest thing, and why we're even having this presentation today, and why I wouldn't have given a talk like this last year, is because new technology is reducing the price of LiDAR very, very, very dramatically. I said $150,000 a year ago, and I said $40,000 now. And the main reason behind that is this. This is the DJI new L1 sensor. And it is DJI's latest LiDAR sensor that attaches to their M300 drone. The L1 sensor is a combined LiDAR sensor as well as a 20 megapixel photogrammetry camera, which is actually the same image sensor that's currently on the Phantom 4 RTK. So it definitely has its photogrammetry chops as well. It is worth noting that their claimed vertical accuracy is 1600ths of a foot. I am always skeptical about that because it is their claimed accuracy in laboratory conditions at 150-foot flight altitude, which is pretty low. And I would expect that not to be quite so good. But that's why we say the 2 to 3/10 real world accuracy on a LiDAR sensor. I do fully expect this sensor to be able to achieve that level of accuracy. It does have onboard RTK and PPK capability, along with the DJI time sync for the lever arm corrections, for those of you that like the technology side of it. And it is super duper affordable by LiDAR standards, at least. The sensor itself is $18,000, and all in for that plus the M300 drone that's required and their incredibly overpriced batteries and all of the other bells and whistles, you are looking at about $44,000 to $45,000 for a full-blown LiDAR system. With all of the hardware and stuff that you need. And it is shipping allegedly by late March 2021. And I'll check my calendar here and see that it is March 29th. And nobody has them yet. So I was actually really hoping to have gotten this before our hands on our sensor before this. So I'd have some real live data from the L1 sensor even to add into this presentation. Because rest assured, we have ours. We have allegedly the first one of the first units to come off the boat. But you know, everyone's been focusing on the ship that's stuck in the Suez Canal, but there are also a whole bunch of ships that are stuck off the port of Long Beach. So we're waiting for our sensor, and make sure to follow us, or you can shoot me an email, logan@aerotas.com, to get signed up for any information on the L1 sensor, because we are going to be running this through a very, very, very rigorous set of accuracy tests, comparing the L1 to the Phantom 4 RTK, to the P1 photogrammetry sensor, and to ground-based surveying as well, and really test out all of these claimed accuracies and see what it looks like in the real world. But the main thing about the L1 and why it's exciting is just because it's fully integrated, so there's no more 18 different companies that you need to bring together on a single drone to get it to work, and it is so much cheaper at 45 grand versus 150 grand that it's starting to become more cost effective where other projects weren't. All right, so that's kind of our hardware overview. That's the state of the art with LiDAR technology. So next up, let's talk about mission planning a little bit. Once you have your drone, you have to actually fly it in the data collection side. And I'm talking about mission planning, not because it's exciting, but because it's really, really, really important. But first, let's talk just briefly, what is mission planning? Mission planning, as I said before, is asking some basic questions like, is this a good site for drone photogrammetry, or is it a good site for LiDAR? Is it legal to fly here? What altitude should I fly at? What's the appropriate overlap? How many ground control points? Where do I set them? How should I arrange the flight pattern? And what data still needs to be ground surveyed? These are very important questions to ask before you do a job site as part of a workflow, because they prevent things like having to go back into the field for field revisits. Those are the biggest time killers out there. Because really, mission planning saves you field time. You have to set fewer control points. You need to do less surveying on the ground. It can save you with time with shorter flight times, fewer battery changes, no field revisits, all of that stuff. You heard me say at the beginning, this should save you time and money. There's so many ways that you can spend more time if you want to, but our goal is to get you the best data while also saving you time. But mission planning also saves you office time too. If you collect the right data, your file sizes are smaller. You can upload them. You can process them more easily. You can extract data more easily. You can actually get better accuracy with less data, which is something that may be a little counterintuitive, but with good mission planning, you can get fewer errors and have a simpler drafting workflow and really get better data with just decent mission planning. And also, it helps eliminate errors. What we've found in our experience is about 2/3 of errors are caused by bad mission planning. Either fly too close to the ground, your overlap's wrong, you didn't set your control right, you didn't fly over your control. These little boneheaded mistakes that a lot of people make, that just little things that then lose you a bunch of time in the field. And honestly, that's true with ground surveying as well as with drone surveying too. Anyone that's ever forgotten to charge their batteries or left a GPS antenna at home and don't actually have the antenna for their GPS unit knows that these little tiny mistakes oftentimes can make the biggest impact. So that's why we say take some time and think about mission planning. But let's talk about some of the main questions with mission planning is it a good site for photogrammetry, and is it a good site for LiDAR? So starting with photogrammetry, well, photogrammetry is really good for projects anywhere from about 1/2 acre up to about 500 acres in size. That's kind of the sweet spot that we've seen. Anything below 1/2 acre, you sometimes can survey it quicker just without even bringing out the drone. So maybe it makes sense, maybe it doesn't. And same thing above 500 acres, it's where it starts to become a little bit more cost effective to survey with a traditional aerial company with a manned aircraft. They can cover, tens of thousands of acres. But below 500, the drone is almost always cost effective. It can make sense over 500 acres, but not all the time. Likewise, up to about 20, sometimes maybe 30 miles for linear assets, the drone makes sense. Beyond that, it may make sense to hire a traditional aerialist. Photogrammetry is very good in low to moderate vegetation. Certainly in more desert areas, you're not going to have that much vegetation, maybe just some low-lying scrub brush. Photogrammetry is spectacular there. Up to moderate vegetation, but if you're in very densely forested areas, particularly in a 7-state survey conference, I know anyone that works a lot in Western Washington has to deal with more than moderate vegetation. Although for any of my friends that are in Nevada and Arizona, well, you don't have a bunch of super dense forests in some places, I guess. But photogrammetry is good for low to moderate vegetation. It does great work with topo mapping, ALTA surveys, getting your planimetrics, volume calculations, et cetera, et cetera. But photogrammetry, as all things, is not the perfect tool for everything. Very large projects, over 500 acres, 40 miles linear, or 100,000 photos, the drone starts to it takes a long time to gather and process the data. Dense vegetation and tree cover, really high accuracy tolerances like ADA ramps where you might need to break out a total station, or there's some railway projects where the actual tracks of a railroad need to be shot in with a total station and be within a few hundredths. Those are definitely not good enough from a drone, as well as indoor underneath overhangs or underneath trees. But that's if it's a good project for photogrammetry. Well, what about with LiDAR though? So let's talk about LiDAR and photogrammetry. Well, LiDAR's huge, unambiguous, complete benefit over photogrammetry is that it provides better ground cover in vegetation. That is the number one main benefit with LiDAR that photogrammetry just can't compete with. This is an actual project here that was flown with both. This is a profile view of a hill that was going down into a stream with a lot of vegetation. I believe this was in Northern California as well. So what you can see is this real world point cloud colors. These are coming from the photogrammetry point cloud. You can see they very densely and clearly map the actual trees, the top of the tree cover here, and they don't have very many points along the surface. These kind of false colored points are going to be the LiDAR points. And while they pick up points up along the canopy of the trees as well, have a much, much better and very clear sense of where the terrain goes along that underneath the vegetation. But as mentioned, it is not perfect. Right here, there is a gap where you can see it is probably some particularly dense vegetation, and the LiDAR unit just simply was not able to see through it. And that's always going to be the case, but like photogrammetry, there are errors with noise where a good CAD drafter can interpolate under that. Even little gaps like this, you can interpolate under it, create a good surface anyway. But LiDAR is absolutely unambiguously better in areas of moderate to heavy vegetation. But I've said before, LiDAR isn't the undisputed king. See, photogrammetry is just way, way, way cheaper still. 45 grand is a heck of a lot for a LiDAR unit, whereas a drone like a Phantom 4 RTK can cost 10 to 12 grand all in, and get you really high quality data, and in fact better data than LiDAR. Photogrammetry also has the benefit of being faster and more accurate on hardscape. And so that's why this is a presentation on a mixed workflow between photogrammetry and LiDAR, because in a perfect workflow, you actually want to combine the best of both worlds. You want to do photogrammetry where you can because it is cheaper, faster, more accurate. That's like everything you want from technology, right? Better, faster, cheaper. And use LiDAR only where the photogrammetry doesn't work, which is going to be those vegetated areas. Sometimes people say, well, why don't I just use LiDAR everywhere? Well, this is why. Photogrammetry is better, faster, cheaper. Even once you own a LiDAR unit, photogrammetry is going to be more accurate than your LiDAR unit, at least until there are more advances in LiDAR technology. That could be a couple of years out. We'll see. But for right now, photogrammetry is absolutely more accurate on hardscape, and LiDAR is better in vegetation. All right. So with that mission planning, now you've gone out, you've flown your site. Honestly, I should point out flying LiDAR is, from a mission planning standpoint, absolutely identical to flying a photogrammetry mission. You draw a polygon, you set your flight altitude, and you pretty much let the computer deal with overlap and everything else. You hit go, the thing flies itself. It's really, really darn easy. So now we've got our data, let's get into the office workflow. So I'm going to start with a high level here, and then I'll actually dive into some of the really nitty gritty of both the photogrammetry and the LiDAR sense side. So an office processing workflow starts with 3D model processing. As I mentioned before, that's kind of your photogrammetry, processing your point cloud. Some people will call that pre-processing for LiDAR. There's no real standard industry term yet. Then what we call drafting line work, that's extracting your vectorized features, your topo points, your polylines, your planimetrics, and getting everything in CAD. With photogrammetry, you got to stitch your photos into the interim files, and that gets you a photogrammetry output, an interim photogrammetry output of a point cloud, an ortho photo, and a digital surface model. With LiDAR, you have some different steps. You have to align and georeference your point cloud. Your flight lines may not always line up perfectly from swath to swath, or from the west side of a project to the east side of the project where you had to move the base station and you have to re-georeference it. You need to align your project. You need to then translate your project to make it align properly with your coordinate system. So if you are working in, WGS84, sure, you can use the raw output, but most surveyors are going to be localizing to specific and known benchmarks. So you're going to have to localize your project by rotating, scaling, translating it to actually match with your known benchmarks and with all of your existing project data. You also have to classify your point cloud, or I guess you don't have to, but it's a very efficient way to get to good data. Classify your point cloud to separate out your buildings from your vegetation to your actual ground surface. Linework drafting is extracting those vectorized features because your point clouds just have too much data, very, very hard to use, too big. And also extracting your vectorized features from each source. So LiDAR and photogrammetry have their different benefits. So you have to extract some vector data from the LiDAR point cloud and some vector data from the photogrammetry point cloud. And you usually need to use an interim software for this, because anyone that's ever tried to put laser scanner data directly into a program like Civil 3D knows that it's an absolute disaster. Point clouds are hard to work with. There's just kind of no way around that. They're tricky. So you usually want to have an interim software in order to extract data from the point clouds. And then you finish it all in CAD. CAD is where you actually bring all of this together. Civil 3D is the most common. Carlson Survey is out there as well that a lot of people are using as well. And there are a couple of other options as well, but it is only in CAD where you wind up bringing, where we would recommend you wind up bringing all of your data together, your drone data, your field data, your photogrammetry, your LiDAR. And that's where you blend it all together to actually create a tin surface, add in contours, add in your site culture, your annotation, seal it, and create that finished survey that is the gold standard of what we're looking at. So if I can summarize all of this in, well, 2 slides now, starting with the photogrammetry workflow. Your photogrammetry workflow starts with your photos, ground control points, and any RTK or PPK data you have. That goes through the step that we call photogrammetry, which gets you an ortho photo, a digital surface model, and Trey, what you were asking earlier, the digital surface model is the full surface that has literally everything in it, including the trees and buildings and stuff you don't want, and your point cloud. That goes through.
There was another question about that, about providing the DEM. Why is that not a standard deliverable for photogrammetry?
Because it takes a human to, or well, it takes work to properly separate the vegetation and the stuff you don't want from the surface that you actually do. And one thing that I use is, well, there are things that very few people want, which are things like if there are cars in a parking site, you don't want that as part of your topo surface. And there are trees, you don't want that as part of your topo surface. But there are actually some exceptions to that, but those are pretty rare when anyone would want tree heights or car counts or something like that. But one great one as an example is, let's say you were actually doing a survey of a landfill, and then part of that landfill, there was a big pile of trash in the middle. Do you include the trash as part of your surface? And the answer is, it really depends. Do they actually want to know the topo surface of the top of the landfill? Or are they actually looking to maybe turn that site into something else and clear the debris? There are a lot of judgment calls that need to be made on what actually counts as part of the surface, which a computer can do very easily, which is include everything. And then the elevation model, which is going to be your clean surface, that really requires human judgment. Not to mention, there are a lot of errors in these automated softwares. They'll take a tree and classify it as a building. They'll take a car, and because it was black, they'll classify a black car as asphalt. And they'll take the roof of a mini mall and classify that as a ground surface, just because the automated processes are not very good for that.
So, but somebody could, if they had a Pix4D license, can generate a DEM or a DTM automatically?
Pix4D does have some ability, to automatically classify point clouds and create an automatic DEM or DTM surface. We have found those are not generally reliable enough for survey purposes and require a heck of a lot of cleaning. And they actually still suffer from many of the other problems that they are very, very, very large file sizes, and they're often in rasterized file format, not an actual clean tin surface that you can then combine with ground data that you can check and merge in CAD. So yes, they are absolutely out there, but they are far from a finished deliverable by themselves. They would still need considerable massaging.
So the goal of a DEM is clean topographic data. And what I'm hearing you say is that's usually best rendered in the CAD package.
Correct. Yep. And kind of as I mentioned before, our workflows, at least our recommended workflows, I shouldn't point them out as the only way to do things. There are other ways to do things. What our workflow is what we have found to be the most efficient way to do things. And the most efficient way to do things is get your orthophoto, DSM, and point cloud, and then extract topo points from that, rather than get a automatically generated digital elevation model and then clean it using manual cleaning processes and running QA on the automatic DEM. You can go that route, and it absolutely is possible to work. We have found it to be more time consuming and error prone in our experience. But we are not if there's a different workflow that works for you, by all means, go for it. We are not the international arbiters of how one must process data, but we are pretty darn experienced. And this is what we've found to be the right combination of accuracy and time savings for surveyors, with a strong emphasis towards accuracy because we are working with surveyors. If we were a GIS company, I would lean a lot more heavily on automated tools, because when you're working in the world of GIS, if something's off by a couple of feet, if there are artifacts here and there, it doesn't matter. In survey, that absolutely does matter. And we really care about accuracy and reliability for survey.
Got a question from the audience here. What software do you use to process LiDAR point clouds?
I have a couple of slides on that coming up, so I will get there. But the short answer is multiple. So photogrammetry workflow is just to finish that up, and I will get into the actual LiDAR software. Photogrammetry creates an orthophoto, DSM, and point cloud, and our workflow is then to go through what we call Linework Drafting, and that actually gets you your 3D topo points, polylines in a DXF format. This is what would most approximate a clean DEM for us. And then that actually goes through CAD finishing, where we take that digital elevation model, which would be a tin surface created from the points and polylines that we extracted from the orthophoto and DSM and point cloud. And then we would put that into Civil 3D to create a final deliverable, which has your surface, contours, site culture, typically in a DWG format. Your LiDAR processing workflow looks fairly similar. You actually start with your individual swath by swath or flight by flight LiDAR data. You still have your ground control and any onboard RTK or PPK and IMU data. That goes through point cloud processing, which again, some people call pre-processing, which gets you a classified point cloud, your LAS point cloud that is properly georeferenced and accurate and classified. Once again, you go through Linework Drafting to extract 3D points, polylines in a DXF format. You will notice from this point, it is the same as photogrammetry. This is where you can merge it with your photogrammetry data, run it through the CAD finishing process, and again, get you to your final deliverable. So those are the two workflows, the LiDAR workflow and then the photogrammetry workflow. They look very similar, with the only the first two steps being difference between photogrammetry and LiDAR. So let's now get into a little bit more of the weeds with both of these, starting with photogrammetry. As I'm sure everyone is aware, photogrammetry is the art and science of making measurements from photographs. It is creating 3D data from 2D photos, with the output being a rich 3D model. Here is your rich 3D model, your digital elevation model, because it includes everything, including contours and a surface around all of these vehicles, which you clearly don't want. This is an example of a digital, this is a digital surface model. I get those confused because they're not super clear. This one is one where a computer could probably identify these as objects, but maybe in some world those are rocks and you actually want to include them. But anyway, this is what your raw photogrammetry outputs typically look like, is a rich 3D model. And photogrammetry, the photogrammetry processing, for anyone that's touched it, they know it takes time. It takes a little bit of human time. Setting up a project in a software like Pix4D is actually fairly easy. Just import your photos, set your ground control points, and blah, blah, blah. But it takes a lot of computer time, especially for bigger projects once you get thousands of photos. And fixing an error, if you do have something that it either didn't process or you're seeing errors on some of your check shots, can take hours or days when you have a project that takes 4 to 8 hours to process. Changing one tiny little setting and trying again can take you another day. So it takes a very long time, and improved hardware can only help so much. But there are different ways that you can process photogrammetry. There are services out there that do automated cloud-based processing. Services like Drone Deploy is a really common one. They're affordable, fast, super scalable, but they usually are very low accuracy with no or low support. Great for when you need just an ortho photo of a site, but typically not going to be up to survey quality deliverables just because of the accuracy. You can also process everything internally by buying yourself a license to Pix4D, buying some computers to run it. Highly customizable and the most control, with the downside being it is expensive with a very long learning curve, and it's also less scalable because if you only have one license, you can only do one project at a time, or maybe two, but it's less scalable when you want to do lots and lots of projects or very big projects, and it's expensive and it takes a while to be trained as a photogrammetrist. Or you can outsource to photogrammetrists like shameless plug, Aerotas. We have licensed photogrammetrists on staff so that you can benefit from all our expertise without the investment. It is flexible with no learning curve, and this is the way to get the highest accuracy, just by having someone that is a photogrammetrist, that is an expert, to get you the highest level accuracy out of your deliverables and the highest reliability to make sure that you don't accidentally process data that is a foot off on half of a project and not even realize it. The drawbacks are it's more expensive and it does take time because you do have to transfer files and on and on and on. For us, at least, our photogrammetry principles are just work smarter, not harder, have an iterative loop. We actually process every single project multiple times to make sure that we have the proper site parameters, camera parameters. We check different settings and permutations of ground control. We check for hundreds of known common errors that we see in different photogrammetry projects to get the highest quality data. And you'll notice that we have a human in the loop. We very much do not believe in just black box processing, that there is no perfect photogrammetry software or suite, at least not yet, where you can throw data at it and it just returns a perfect point cloud every single time. We very, very much believe in human in the loop for all of this so that they can run QA, QC at multiple steps to run your quality assurance steps to actually get a high quality deliverable. We often get questions, hey, you process a billion, tens of thousands of photogrammetry projects. What hardware do you use? Well, we don't actually hide this. We use, this is a sample of one of our more recent processing servers. We have a whole bunch of processing servers, but for anyone that's familiar, you'll look at this and say, this is actually reasonably accessible technology. It costs about $3,000 to $4,000 for a good computer with some of the latest processing servers out there, but it's also not your highest quality, $20,000 specialized servers, because we have developed a parallel processing workflow that, generally speaking, for larger projects, it makes more sense to process a larger project across 4 fast computers than 1 supercomputer. So parallel processing is a big part of our workflow, at least, on how to scale and improve the time efficiency of all of these things. So when you have very, very large projects, you can have multiple photogrammetrists, multiple computers working on it all at once to really dramatically cut down processing time, rather than trying to spend tens of thousands of dollars for a 10% improvement in hardware. Because with photogrammetry processing, to get good data, it's not about the settings, it is about the right workflow. Having a standardized workflow, utilizing checkpoints to validate your data, constantly checking for errors, adjusting settings based on the site, and getting trained on photogrammetry. We are proudly powered by Pix4D. It's our primary photogrammetry engine. But getting trained on photogrammetry, it will do much more than any sort of new software or new computer. And also, don't forget to manage your processing time. Most of the issues with photogrammetry are determined in mission planning. If you're taking too much time in processing your photogrammetry, there's a good chance that you're just collecting too much data in the field. Processing time is nonlinear. If you double the amount of photos, you're actually going to 4x the processing time. So cutting down on the number of photos you take in the field while still being within a proper level can get you the best overall workflow and results. And at the end, a good workflow is much more effective than having a good computer. That means both the field and data collection workflow, as well as your office workflow. Staging your processing, running it in parallel with other people, running a step 1 initial pick parameters multiple times, and then scaling up all helps you to reduce overall photogrammetry processing time. And if you do want to get more into photogrammetry, you should check out the ASPRS. They are a nonprofit organization, the American Society for Photogrammetry and Remote Sensing. They are not a sponsor or anything, but we are not sponsors of them, other than just being huge advocates of them. They provide a lot of educational resources to the entire photogrammetry and surveyor community. So ASPRS is a great organization, and we recommend if you want to either get certified as a photogrammetrist, they're the ones to look out for, or if you want to find a photogrammetrist, they can help, and you can get trained as a photogrammetrist as well. All right, so that's photogrammetry. Now let's get into LiDAR processing, which is probably what a lot of you guys are interested in. LiDAR processing, the main goal is to go from a raw proprietary data format to a clean and useful data point cloud.
That might be, I've got a question here for you, Logan, and this might make sense
Please.
now. You had mentioned a properly referenced point cloud. Could you talk about the definition or the description of what a properly referenced point cloud is?
Absolutely. So a point cloud is just by definition any set of points. It can be anywhere. You could use a phone or photogrammetry to create a point cloud of whatever room you're in. A properly referenced point cloud is one that is geo-referenced to known coordinate systems. Now, that can be in either a NAD83 datum that you are using for a project site, or referencing it to known control points. When you're working with survey, typically you're going to be working with existing data, existing benchmarks, existing monuments, existing control or control networks, and you want to geo-reference your point cloud so that your point cloud data lines up perfectly with all of the other data that's been collected on that site. And that can't always be done just by, perfect GNSS processing when you're localizing to a site, especially if your site data is itself perfectly local, where you have a single point that's maybe 5,000 northing easting, and you've shot everything with the total station. So you have to geo-reference your point cloud to actually get it to line up with all of your other data, such that anything that you extract from the point cloud matches with all of your other data, or is in the same coordinate system, the same datum, that it all aligns, and you don't have, when you import it into CAD, points that are a million feet apart from one another, which very often happens. And part of the reason this is so important is, again, anyone that's ever flown data with a drone, or anyone that knows the ins and outs of GPS, you know that getting points to align and localizing on a project site is really important. If you don't properly localize your project site, you might wind up with every single point being a foot north of it, of all of the prior points. Or you have two survey crews shooting the same point and all of their data is offset by a couple of feet. That absolutely happens with drone data and with LiDAR data as well. So georeferencing, it's a really critical step. So in LiDAR processing, you've got to go from that raw proprietary data to a cleaned, useful georeference point cloud. The first step, the pre-processing step, is tricky, and it's going to be different for every single hardware stack, especially, as I mentioned, the drone LiDAR market out there is so fragmented right now that I don't even know all of the different LiDAR integrators that are out there. And a lot of them require proprietary software. So I'm going to focus a lot on the DJI L1 sensor, because we have been able to see that data, even though we haven't done our own test data at all yet. And I should point out, this is still a work in progress. LiDAR is still a new technology, and the ideal workflow is likely to change over time. I bet, hopefully, if I'm lucky to get invited to speak at this conference again next year, I can talk about all of the changes that I've made, that our company has made to LiDAR processing. And I can make fun of myself for all the things I said this year that I'm like, wow, that's how we used to do it. And that took way too much time, and there's a better way to do it. So hopefully we'll have that next year. But your general LiDAR processing workflow looks like this. You start with processing all of your GNSS and IMU data. That's your RTK or PPK processing, along with your inertial measurement unit. That can help you align your swaths so that your point clouds, when you have multiple swaths that might be offset, you align them into a single LAS point cloud that is cohesive. You then geo-reference it. That's where you translate your point cloud so that it aligns with your existing coordinate system. That may entail translation, rotation, or scaling. You then want to verify your accuracy. We very, very, very strongly recommend verifying your accuracy before extracting any data, and then classifying and filtering your points. So let's go into each one of these 5 to a little bit more detail. Starting with your GNSS and IMU processing. Like I said, this is the step that's most dependent on the hardware that you use. For the L1, this has to be done with DJI Terra software. That's DJI's proprietary software. And if you don't like having to buy another piece of software, well, you're not alone. It's kind of annoying, but LiDAR systems, when they record their data, it's typically in a proprietary format that needs to be processed against the IMU. This is what the DJI M300's LiDAR data looks like when it comes out. You have this, which is all of your GNSS data. It's raw inertial measurement data, your actual Rhinex observation files from your base, as well as from the aircraft as well. And you combine it with the raw LiDAR data to actually get a cohesive single point cloud. Now, again, this is what we would still call a fairly raw point cloud because it's not yet geo-referenced. You may need to do that rotation, translation, and scaling. And also, you have to align your swaths. When you fly either multiple flights on a single day or across multiple days, they may not align perfectly. This is, again, some real-life LiDAR data where this is the exact same hill, but flown before we've done any swath alignment. And you can see that there are some serious, oftentimes multiple feet vertical differences from one place or from one flight to the next.
And which software are you using for this step?
For aligning swaths, this would be done in TerraMatch. It is also possible to do this in a software like Global Mapper and their LiDAR module as well. But you do want to align those swaths and get everything aligned perfectly. As for georeferencing, that's the best way to do that is the same with traditional drone photogrammetry is georeferencing using point clouds. So you want to localize to your project or using ground control points. So georeference using ground control points. You can also even compare the LiDAR data to the photogrammetry work point cloud as well. But there are some challenges here. So this was a really funny one to actually create the screenshots for, because this is what the photogrammetry point cloud looks like. And this is what the LiDAR point cloud looks like in the exact same area. I promise you, I actually spent a lot of time making sure that I took the screenshot of the LiDAR points in the exact same area as the photogrammetry point clouds. There was no need for me to do that because it looks absolutely identical and you can't tell. And that's actually a really big challenge with LiDAR is raw LiDAR data is uncolorized. It's just a bunch of points with elevations. And so if you are trying to georeference, with the drone point photogrammetry point cloud, you can find the center of that point really easy. And you can localize your XY shifts very easily. Well, you can't find a XY point here at all. And that means because this was on a slight slope as well, you can't actually localize your Z either. You can't just shift it up and down. You don't know if there's any translation at all. And that means in uncolorized point clouds, it can be very challenging because you often have to use a least squares error correction software to try and scale your raw LiDAR point cloud to known points in order to get it properly localized. Thankfully, with new systems like that DJI L1, because it has a LiDAR unit and a camera on the same unit flying at the same time, as part of its post-process or pre-processing software, it actually is capable of creating a colorized LiDAR point cloud, which should make it much, much, much easier to localize in the X and Y direction. We are certainly still going to test that a little bit more to see exactly how accurate the colorization of the point cloud is. But that should actually help you with GCP marking as well as localizing your project using GCPs. For georeferencing point clouds, it's worth noting a lot of LiDAR systems that we've seen to date and what people are using rely super, super heavily on GNSS and can oftentimes the LiDAR service provider, the people that buy and export operate some of these LiDAR things will only export in WGS84 because they don't know the first thing about localizing a project site to survey coordinates. And oftentimes it's actually pretty poorly localized even to WGS84 because they don't actually know how to set up control network. So we always say whenever you're doing something for survey, always you should still use check shots to verify vertical accuracy. It is very difficult to localize existing data, and any of these ones that rely purely on GNSS and not ground control or check shots, it's quite unreliable because if the GNSS doesn't come out perfect and you just see errors, there's not a lot you can do. You have to refly it. So, but if you are using control and if you are using an appropriate number of check shots, then if there are errors, you can actually identify the source of that error and then remove it. Same thing if you fly it simultaneously with photogrammetry, by comparing the two sources, you can identify sources of error and correct for it. So georeferencing your point cloud is important. You can compare LiDAR and photogrammetry clouds, utilize a colorized point cloud when available, and you also can use 3D targets. There are a few people out there that have created some 3D targets capable of being identified by LiDAR units. And then step 4 that we put in here is verify accuracy. People skip this step a lot, and that's the most irresponsible thing you can do. You should absolutely verify accuracy on all projects. As a photogrammetrist that works with client data, a lot of times people say, well, how can I trust that your data is accurate? And my answer is always, don't trust me. Verify it, check shot, keep check shots, hold it back. I don't expect anyone to trust that my data is accurate. And if you come across a surveyor that's like, or a surveyor, a service provider you can trust the surveyor's seal, or at least you should be able to trust a surveyor's seal. That's why we're all here at this conference. But if you have a drone service provider that says, oh, just trust it, I know what I'm doing, it's got good GPS, you can trust its accuracy, I would set a couple of check shots. A lot of people overpromise on accuracy. As I mentioned, when measuring accuracy, some people say, oh, it's accurate to 5,000th of a centimeter. That's clearly junk. No surveyor would believe something like that. So use checkpoints. You can compare to a photogrammetry point cloud. But for us, our kind of North Star when measuring accuracy is the ASPRS Positional Accuracy Standards for Geospatial Data. It's a set of academic research and guidelines for how to measure and report accuracy. And it actually applies to all digital geospatial data. So that means both photogrammetry and LiDAR, both are included in the ASPRS standards. Back to the ASPRS, great nonprofit organization. So check that out if you really like reading about accuracy verification standards. And then your last step, only once you have that proven accurate point cloud, then you should start actually doing work on it by classifying and filtering the actual point cloud. There are a lot of automated classification systems, like from Global Mapper's LiDAR module, or TerraScan has some as well. I know there are a bunch of other LiDAR softwares out there that can filter out things like vegetation in green, and then gray and orange are just kind of different noise, and ground in brown here. This once again shows how it is imperfect, where there are still gaps in the ground data, but you can actually get rid of a lot of that vegetation very easily through some automated systems. Once again, it's not perfect, but it actually is very good, and it is certainly a useful step when starting your LiDAR processing, is to classify your point cloud automatically and remove a lot of the vegetated surface. So as Trey was asking, what does a software stack look like? Here's what a sample software stack might look like for flying a drone with the DJI L1 sensor. I should point out, this is a sample. There are lots of softwares that can do this. You are not forced into using exactly this software, with the exception of step one, which does have to be done in DJI Terra. This is the pre-processing. Again, if you're using a different sensor, there will likely be a proprietary software for whatever hardware you're using. You align swaths in a software such as TerraMatch, georeference your point cloud, and in something like Global Mapper's LiDAR module. You can verify your accuracy in good old-fashioned Excel, where you export your points and compare them to your known points. That's sometimes the best way to do it. And you can then get your point cloud back in a system like Global Mapper to actually classify and filter your points from there. So that is our kind of LiDAR processing workflow. And one of the things that's most interesting is, gosh, it's already 4:40, and I haven't even talked about how to extract workflows for extracting data from a LiDAR point cloud. And that's because, well, while that's really important, it's secondary to actually getting your point cloud right, getting all of your data right beforehand. So often we see LiDAR providers that then have a set of LiDAR that isn't even good. So if you extract data out of it, it's not even worthwhile. And thankfully, Linework Drafting is something we've talked about a lot, and it's a lot more of a known quantity, whether it's with LiDAR or photogrammetry. Linework Drafting is reducing the rich model to a CAD-friendly surface, because photogrammetry and LiDAR outputs by themselves are too big for CAD, and you want to reduce it to CAD compatibility. It's necessary because these files are too big. Your raw LiDAR outputs are many, many gigabytes. Too much data you don't need, like lots of points on those leaves, lots of noise, and not enough data you do need. In Linework Drafting, well, how do you decide LiDAR or photogrammetry? Our recommendation is start by deciding LiDAR versus photogrammetry before you start any of the drafting. Our recommendation is to do as much drafting as you can from a photogrammetry point cloud first, and then go into LiDAR to extract data where you can't. And that is because, as I've said a couple of times before, the photogrammetry data is tighter. This is another project that we've worked with that had both photogrammetry and LiDAR. What you can see is this kind of beige colored point cloud is from photogrammetry, and that's a very tight, neat line. These yellow points come from the LiDAR point cloud, and if you can see vertically that there is about 3 to 4 tenths of a foot of just noise on that LiDAR point cloud. Now, you wouldn't really care about the roof of a building. This is just to make it something that is interesting and that you can see clearly from profile view. But the same thing is true on asphalt, that the photogrammetry point cloud is going to be much tighter, much less noise, and overall more accurate by a couple tenths of a feet. So that's why we always say start by drafting on photogrammetry and then extract LiDAR data where where the photogrammetry is obscured by vegetation. As for what if the point clouds don't agree? Well, they should if you actually followed all of my previous steps. But if they don't, this is why you have need for QA/QC standards and for checkpoints as well. By making sure that if you have points that are on the ground and they're about half a foot apart from each other and there's no overlap, well, one of those systems is wrong and you might have to go back into processing. As far as different methods of drafting the line work and extracting it, we have what we call OK methods. There's no perfect method. These are all somewhat time consuming. You can draft on individual photos directly on the ortho photo. You can go into the point cloud again through systems like Global Mapper or even like Autodesk Revit can do this sort of thing, extracting data from the point cloud. You can convert the point cloud into a surface once you've done your data extraction, or once you've done your point cloud classification. That's one that we actually really like, is classifying it, creating it into a surface, and then extracting additional topo points and break lines from a classified LiDAR surface. And then you can draft directly on a 2.5D orthophoto and DSM. However, I should point out there are a couple of bad methods that we don't recommend for extracting vectorized features from either LiDAR or photogrammetry data. First off, importing any of the raw data into Civil 3D is a nightmare just because you actually typically have to reduce its quality so much. We spend all this time getting, 1 to 2 tenths of a foot accuracy, and then you just start downsampling all of your imagery, or worse, dumb decimation of a point cloud. That's what we call it when someone's just like, oh, delete 90% of the points just so it can work in Civil 3D. We think that's terrible. Don't do that. There are better ways. And again, you usually have to use an intermediate software. That said, there are a lot of options for line work drafting. Same with photogrammetry. There's automated software analysis out there that'll try to automatically vectorize a point cloud. It's cheap at scale, but we really don't like it. Once again, for survey, it can give you a good idea of where certain project lines are, but there's so much noise and so many errors. It requires so much QA/QC to get it up to survey standards that we're not a fan. You can draft all of it in-house yourself. You have the most control that way. You have high accuracy, a reliable known product, but the labor is typically expensive. For if you're a surveyor and you're just sitting there drawing paint stripes or extracting topo shots out of a point cloud, that's expensive labor. And it's very time consuming. Or you can hire an expert, again, shameless plug, like Aerotas, where we have photogrammetrists that work on photogrammetry, CAD techs that work exclusively on extracting data from point clouds, and then our CAD drafters that actually bring it all together in CAD. And that makes it much more scalable and affordable because we have all of the excess capacity to do that. But the downside being you, of course, have no process control. Next up, we had questions about what software can you do line work drafting in? And like I said, the answer is a lot. A lot of softwares can do it. The problem is these are all very expensive. And to be honest, we haven't really found a favorite yet. We like Global Mapper and Virtual Surveyor and Revit all work. But this is, if ever there was a slide that I'm probably that I can almost guarantee will be dramatically updated next year, is once we really start saying, okay, we've done, a couple dozen line work projects. Now, how do we start doing a couple dozen a day? That's when the software really starts to matter in terms of your time efficiency, and where I'm sure our economies of scale will allow us to get a much better answer as to what's really the most time efficient software out there. Right now, the reason that none of these softwares is perfect is because line work drafting takes a lot of time. It doesn't actually take that much computer time once you've processed your point cloud, but it takes a lot of human time, followed by even more human time. It requires a lot of quality assurance, QA/QC checks. Whether it's an automated software, they make more errors than humans. Humans actually make a lot fewer errors than the automated systems right now, but they still require QA/QC. And unfortunately, there just no magic solutions to it. As part of a good CAD drafting, one of the things that can make it more standardized, more quick, and with less QA/QC is having a robust set of CAD drafting standards. That's everything from what layers you use to policies and procedures for, okay, what's your density of topo points based on vegetation? How do you deal with cracked line work? How many different lines are you drawing for curbs? How do you interpolate underneath trees for curb lines and that sort of thing? So obviously having your CAD standards is an important part of just efficiency, but also standardizing your process to get that reliable, high quality deliverable every single time. And then once you get into CAD, once again, your final slide is just a finished survey. That's bringing all of this stuff together, your photogrammetry points, your line work, your LiDAR points, merging your field shots and your drone data. As I've mentioned, the drone photogrammetry and LiDAR is a tool. You still need field data, particularly things like boundaries, building corners, monuments, ADA compliant areas, or obscure areas are typically still going to need to be shot on the ground. You can bring it all together, create a surface in CAD, make yourself a tin surface, add contours to it, apply in all of your custom layer templates to make sure that it works right. Improve visibility and usability, adding in your blocks, symbols, things like that to actually make your survey useful to the end client. And another big part is adding in your CAD-friendly imagery. These files have always been so huge, but you don't want to throw away your imagery. What you want to do is actually create CAD-friendly imagery that utilizes good compression algorithms so that you can get high-resolution imagery in a CAD package that is still a downsampled version that can be transferred easily. It's worth noting this is all, when we say CAD friendly, we do use lossy compression algorithms. So you do lose a little bit of the fidelity of the high resolution drone imagery, but it is optimized for just context, having that site background on a project site. To get to your final survey deliverable, which should look the same, whether it was made conventionally or with a drone. And so just to wrap things up before I fully open the floor to questions, all of this, again, when I talk about workflow, it's about saving time and money. I've said this before that we're not the absolute authority on how to process data. Everything that I've just said is what we've learned as our best practices so far for how to have a good workflow that can save you both time and money. And a big part of that is not always using a drone, picking the right tool for the job, whether that's a Phantom 4 RTK, or maybe it is an M300 with the new L1 LiDAR sensor, or it's time to break out your total station. The drone is not the right tool for every job, but it is a tool that we think should be in every surveyor's truck because it is so worth it in so many different projects. Make sure you do utilize a complete workflow. Every single one of these steps matters, and there are pitfalls at every single one of these steps. Pitfalls that cost time, cost money, or can require field revisits. So use a whole workflow to actually get high quality data. And with that, I will open up the floor to questions that anyone might have. And I should also point out, if you would like to receive, a copy of this presentation, if you have any questions, if you want to see demo files of what some of our deliverables look like with all of that, please feel free to shoot me an email. My email address is just logan@aerotas.com, and it's up there on the screen. And if you do have any questions, please do drop them in the chat or in the Q&A session, and I would be more than happy to answer them.
Real quickly, so you were talking about compressing those large geotiffs into a CAD-friendly format. What kind of compression algorithm do you recommend?
Yeah, so there are a couple different versions you can use. Standard TIFF and JPEG compressions work using, there's a lot of open source software out there that can do it, but those are not going to be the most efficient ways. Our favorite is one called ECW, an enhanced compressed wavelet format. It's a proprietary software that does cost a decent amount of money just for the license to create these ECW files, and they are a little tricky to use. So for us, we actually package them in as part of a cohesive CAD file. So we actually integrate it directly into CAD because it's not a very common image format. The reason it's not common is because it is designed for compression of very large geospatial images. So It's certainly not like your JPEG or something. So ECW is our favorite. It's not the only one out there, and it is a proprietary software that costs a lot of money, so it's not right for everyone. But it is what we use for delivering all of our projects to our clients.
We were chatting about DJI products on government jobs for county government agencies. I know you follow this very closely. Can you talk a little bit about DJI and the government?
Yes. Oh, that's a messy relationship. DJI is unfortunately the leader right now in the drone world. And in projects where you can use DJI, it is going to get you the best accuracy at the lowest price. However, as many of you are probably aware, there are some government restrictions on that. Now, oftentimes the restrictions are a little weird. Most of the restrictions, most of the time, only restrict the government, federal government agencies from operating DJI products directly. They do not prevent third-party surveyors from operating DJI products on government properties. There are a couple of exceptions to that. Typically, if you are flying on a military installation or a Department of Energy facility, then maybe they will not allow DJI products to fly at all. But a lot of times you actually can fly a DJI product for federal government projects and state government projects. It is just the federal government agencies that are not allowed to.
What about local governments, like say a county?
Most of the time they actually allow it. I don't know every single county government regulations. Counties can make their own rules, and they may, in fact, ban DJI products. But in our experience, generally speaking, the regulations are at the federal level, not at the state or local level. And it's worth noting, there are some other drone companies out there that make LiDAR systems or photogrammetry systems that are fully Department of Defense and, insert three-letter government agency, fully compliant with all of that stuff. They're going to cost a lot more money, be harder to use, and get you pretty much the same data. They are not just going to be outright better. They're the market leader as far as this technology goes. So there are other options out there, but if you can avoid them, we think DJI is unfortunately still the best. I can't wait until they get better competition, honestly. I'd love to see more, because that just brings the price down for everyone, is to have more high quality systems out there.
Switching gears a little bit, what are some of your favorite 3D targets on the market? Seems like utilizing building corners could be useful.
Oh, for LiDAR, for targets for LiDAR, yeah, building corners are useful. If you can extract the top of any sort of kind of, I don't know how to describe it, pyramid-shaped object, different like stone pillars a lot of times are very easy to see. Physical monuments that actually do set up large, curb humps, anything that is a physical 3D object is very, very good to shoot and can be used as LiDAR. You can even set up, I know there are targets out there that are drone targets that are on little tripods that raise up about a foot off the ground that you can then shoot in and use as a target for LiDAR in a non-colorized point cloud. I'm hopeful that the need for that will go away as colorized point clouds become more common and become more reliable.
So going back to DJI, this seems to be popular.
Mm-hmm.
Why would you only ban DJI and not other Chinese manufactured drones? And can you confirm that DJI, does anybody know, do they actually take, quote unquote, the imagery and disappear with it? Like, do they actually, the images on your SD card?
So I can tell you there is absolutely no evidence that anyone has discovered that DJI takes any data. And a lot of people have done some detailed audits on this. As to why it is just DJI and not all of the other Chinese manufactured drones, this is dangerous because I'm going out of the realm of photogrammetry, which I am an expert in, and starting to talk in the realm of politics, which I am not an expert in, because it is a political decision. It was a decision made by politicians for political reasons, not by scientists for scientific or technological reasons. Beyond that, I can't say too much, but that's the answer. It is a political reason, is because they are a very large market dominant Chinese company, not because there has been any evidence so far of DJI actually abusing or stealing data. DJI has hired other third-party companies to do data audits. Whether that's trustworthy, that's honestly up to you to decide, but we have a lot of faith in the technology, at least as far as getting high quality data. That said, again, if you actually were doing a mission on a US Air Force base with a whole bunch of parked B-2 bombers, you know, I would probably not fly a DJI drone over that job site either.
Earlier, Gary was asking, we were kind of talking about the flight plan best practices, and you had mentioned not bumping your overlap up too high. Gary was saying that he gets a lot less noise with higher overlaps. What are your thoughts on that?
Site dependent. And also it depends on what you mean by high. So our recommended level of overlap for photogrammetry purposes is 75% front and 75% side. That we have found is a fairly good Goldilocks area of good enough without being overkill. And there's a range there. If you like 70% or even up to 80%, you're actually still in the kind of good range. Anything lower than 70, we think can lead to some problems. And anything over 80, we have found it doesn't actually increase data. And depending on the project site, higher than that actually can create erroneous matches. If the photos themselves are too close together, photogrammetry software can create a match based on photos that are very close to one another, and that can introduce a whole lot of vertical error and actually create additional noise. So it is a little bit dependent on the job site and your flight altitude, but in our experience, anything above 80% does not improve the bottom line accuracy of a final survey, but certainly does take longer and increase processing times by a significant amount.
And about the actual hardware, when we're looking at the photogrammetry workflow, can you really use any drone that has a camera, Mavic 2, or even a Mavic Mini?
So technically, yes, but not all cameras are created equal. Photogrammetry can work with any imagery, but the better quality camera, the better quality the results are going to be. Typically, the Mavic 2 Pro is about the lowest end drone that we would recommend for survey grade photogrammetry. If you use a Mavic Mini, well, for one, it can't actually run autopilots to fly automatically, but it also has a very, very small rolling shutter camera with a lot of noise that even if you were to process it, you'd be looking at best half a foot accuracy, even with a lot of ground control points. The Mavic 2 Pro, even that has what's called a rolling shutter. It creates a lot of noise. You're looking at, 0.3 of a foot error, even with perfect procedures and ground control. The Phantom 4 Pro V2, that one starts at about $1,500. That's where you can really start getting survey grade accuracy. And just because it is a global 20 megapixel global shutter camera, it gets better. And it goes all the way up to, I actually have one right here. This is the latest and greatest in photogrammetry sensors. This is the DJI P1 45 megapixel photogrammetry specific sensor. This is a fun one that we just recently got, and we're actually doing a lot of testing on it. So if you want to know more about this, shoot me an email and we'll send you all of our tests once we're done testing this thing.
Do you have any thoughts, comments, or wisdom regarding merging drone photogrammetry kind of for the open sky portions of the project with the SLAM LiDAR for under tree canopies?
Yeah, so typically I've said a whole bunch of times, it's probably sunk in by now, LiDAR is better in vegetated areas, photogrammetry is better in hardscape. Typically, start with your photogrammetry point cloud or your photogrammetry data and draw boundaries over where it has good data and where it doesn't. Where it doesn't have good data, import that boundary into your LiDAR point cloud and say, this is where I'm extracting LiDAR data. This is where I'm extracting photogrammetry data. Split your workflows and extract the photogrammetry first and the LiDAR second, because the photogrammetry is going to be higher quality where it can. And then you use the LiDAR data to fill in the gaps. That is typically our workflow. If you are working in any of these softwares, they are all capable of exporting shape files or KMLs or boundaries from one to another, assuming you know your file formats. So that you can actually easily transition from one software to another to extract data. But we say start with photogrammetry, export data in high quality areas there, and then move to the LiDAR point cloud to extract the areas where it missed.
What type of accuracy can you expect if you were to draft planimetrics strictly from the CAD-friendly ortho?
That's a great question, and it depends very heavily on how big the site is. If you are doing a very small site, and I'm saying small meaning like 1 or 2 acres, the imagery will be small enough that you can import it without needing compression and you aren't going to lose data. So you can actually probably still get about 1/10 of a foot accuracy on very small sites. The larger the site, the worse accuracy you're going to get. If you get up to something that's about 100 acres or so, you're going to have to compress that image so much that you're probably going to see about half a foot worth of accuracy issues when compressing it. When it is lossy compression too, because of the way these compression algorithms work, it's not just bigger pixel sizes. You actually sometimes can introduce some slight translations as you are moving. If you make the pixels more than a fixed integer number bigger, then they actually shift them a little bit and it can offset it. So what our recommendation from a workflow, in fact, this is probably the better answer. If your question is, what can you get from drafting off the CAD-friendly ortho? Our answer is no, don't draft on the CAD-friendly ortho. That's a bad workflow. Measuring the accuracy is secondary because it's going to be worse. What the proper workflow is to draft on the full resolution ortho photo. Utilize a software, utilize an intermediate step so that when you're doing drafting, you're actually extracting it from that highest resolution site. There are softwares that can do it. Like I said, any GIS software is capable of handling very large photos better than Civil 3D. So again, Global Mapper, ArcGIS, and Virtual Surveyor are some of the ones that can handle these large image files a lot better. That's really where you should be drafting on the ortho photo. Do all of your drafting on the full resolution, not on the CAD friendly. In fact, that is just policy here. You do not draft on CAD friendly ortho photos here at Aerotas. No one does that because you spend all the time getting accuracy and then you're just throwing it all out the window. So
that CAD friendly is really just for context and good looking imagery to back the drawing. If you're trying to extract data, you should use the full resolution GeoTIFF in something like Virtual Surveyor. Is that correct?
That's absolutely correct. Yep.
Gotcha. I got 3 more questions for you. What impact might you anticipate with the publication of the 2022 datums?
If you know GPS, not much. You should actually be able to process everything and convert everything. I should point out, I know a lot about GPS, but I also know enough to know that I am not the leading industry expert on GPS, as good as I am with drones. We expect there to be no major impact, though, with accuracy. There may be some more common issues where people localize to the wrong site, that sort of thing, but it shouldn't actually be a dramatically different set of processing standards than anything else, as most of this is going to run through very mature GNSS processing services that will be updated with the latest datums.
Gotcha. So talking accuracy, do you try and meet ASPRS standards with every flight regarding accuracy standards and 95% confidence, or does it depend more on the expectations from the client and project?
So our internal goal is, yes, we plan to meet the ASPRS accuracy standards on every single project. Now, for anyone familiar with it, there are actually 2 sets of ASPRS reporting standards. There's one that's called a produced to meet standard, and then there is a tested to meet standard. Our internal thing is that every project will be up to that produced to meet standard, which means that we will use processes and procedures to get a certain level of accuracy, typically 1 or 2 tenths of a foot on every single project. But we will not test it and verify it at that level of accuracy because that is another very time-consuming step to actually test and prove the accuracy on an individual site. But as far as whether or not we do our best to achieve that, yes, we try and meet ASPRS accuracy standards based off of our photogrammetry knowledge and experience on every site. And it's another policy of ours is we don't give bad data. If a client sends us data and we find errors and think it might be a couple feet off, we just won't deliver it. That's how we see things. And that's part of our just kind of compliance with ASPRS is that we really don't give out bad data. And if we think it won't comply to a reasonable level of survey grade accuracy, then we won't even deliver it.
Also, I'll put a link in the chat. Logan wrote an article on kind of what is survey grade accuracy that goes into a little bit more depth about how that's defined and how those requirements for survey grade accuracy can even vary by project.
All right.
Last question for you before we part here. Do you do presentations for federal agencies?
I'd be more than happy to. Yes, we do. We give presentations to everybody. We're actually really proud. So I'll take this moment to give another thanks to John Luckow and people like John everywhere at the whether it's from Washington or California Land Surveyors Association or anything like that. We've been partnering with surveyors throughout the country for years, and you guys have been supporting us as making sure that we try and support the survey industry as well. So thank you all for participating. And like I said, please do, if you have any questions, or if you think maybe you want to work with Aerotas in the future, please reach out, and we'd be more than happy to help. And with that, I will let everyone go off to what I think is the next happy hour on the list.